Welcome back, everyone. In this video we're going to be looking at simple harmonic motion, and so this is number 73 from chapter 14. And so we have a 10 kilogram block which is on a frictionless surface, and it hits and sticks to another 10 kilogram block, and then they undergo simple harmonic motion. So we are asked to find, first of all, the amplitude of the simple harmonic motion, and then in part B we want to find the frequency and the period of the motion, and then also the time to return to the point of impact. Okay, so for part A, first we have to find out how fast the blocks will be moving, and so we want to use momentum conservation. It's an inelastic collision, so we can just use momentum. So m1 v1 plus m2 v2 initial is m1 plus m2 times v final, and so the speed is just going to be 1. Okay, that was pretty obvious. So now what we do is we think about energy, and so we can say that the energy initial is equal to energy final, and now I choose initial to be when the two blocks have stuck together, and the final I could choose any place I like, but for this what I could do is when we have maximum compression. When we have maximum compression of the spring, this is going to give us a speed of 0. Okay, so this is going to be immediately after the collision. Okay, and so we can say that kinetic plus potential equals kinetic plus potential. And in this case, U is the spring potential energy, 1/2 kx squared. Okay, so the starting kinetic energy is 1/2 times 20 kilograms times 1 meter per second squared, and the starting potential will be 0 because the spring is unstretched, and then the final kinetic will be 0, so these two quantities go to 0, and the final potential will be plus 1/2 kx squared. Okay, and when we set this up, we know that k is actually 110 newtons per meter, and we find that x is equal to 0.426 meters. Okay, now if you think about it, that's actually the amplitude of the motion, because when the two blocks hit and stick together, that is their initial state, so that's kind of the equilibrium, and then what's going to happen is they're going to squish together, and they will have traveled an amount x, which is equal to their amplitude when their speed is 0. And so if we simply say that the energy, the kinetic energy that they had here is equal to the potential that they had here, that's kind of what I'm doing, then now we have the amplitude of the motion. Okay, so in part B we're asked to find the frequency, and in order to do that we need to find the angular frequency, and for a mass on a spring this is given by the square root of k over m. And just as a reminder, what this comes from is we're trying to solve an equation such that the force itself is equal to mass times acceleration, and the force is the spring force, negative kx, and then a is actually the second derivative of x with respect to time. So this is presented in the book in a little bit more detail, and this is how we find basically that x is equal to a cosine of omega t plus some constant, where omega is this square root of k over m. So we simply plug in square root of 110 over 20, and we get omega is 2.35 radians per second. Now to convert that into frequency, we remember that frequency is omega over 2 pi, and this gives us a frequency of 0.373 hertz. And of course the period is 1 over that frequency, so the period is 2.68 seconds. So finally, if we want to find the time for the system to return back to its equilibrium, well, how much of a cycle is that? So if we look at the x position versus time, we're going to have something that looks like this. Okay? And what we can say is that basically this is when we get back to where we started. This is the amplitude of A that we calculated previously, and so that means that we're talking about a time of 1/2 the period, so that's about 1.34 seconds. Okay, so that's it for this one. I hope that these mechanics videos have been helpful. If you have suggestions or requests for other types of problems you'd like to see solved, just shoot me an email and I'll see what I can do. Thanks.